Hello 8th graders, you have made it to Unit 4. We're going to start in on this unit about work and power, and the way we're going to do that is by starting with these ideas called potential and kinetic energy. I'm pretty sure that you have discussed these topics before in 7th grade, so hopefully some of this will feel like a little bit of review, but if you haven't or don't remember, we're also going to pretty much start at the beginning with these topics as we learn about them now. Before you get going, you need to make sure that you have gone to finish the warm-up, which is a Google form in Google Classroom. If you haven't done that yet, make sure you pause this video, go do that now. You will also need your notebook for today. Make sure that you have a nice clean piece of paper with a notes and practice side ready to go. And you should label the note side Unit 4, Part 1, Introduction to Potential and Kinetic Energy. Here we go. Your goal today is to be able to do two things, and they're very similar. So your job is to be able to explain the relationship between mass and velocity when it comes to this idea of kinetic energy. Mass and velocity are the only two things that are in this. This is an equation. They're the only two things that are in this equation. And so you're going to also be able to calculate when you're done too. You're also going to need to do the same things for potential energy, but with the things that are in that equation. Mass, height, go in potential energy. So you're going to calculate that one also. So potential energy and kinetic energy are these two types of energy that are kind of like categories. Every other kind of energy that exists is either a type of potential energy or a type of kinetic energy. So when you think about like the power that are keeping your lights going, or the gasoline in your car, or any other type of energy that's out there, they're all types of one of these two. And so that's why they're kind of important to start with when we're talking about energy and the whole topics of this unit. From your warm-up, your job was to figure out what would it take to make Stu really go flying. And you've got Fonzie here jumping on the other side of a teeter-totter. These two characters are dealing in potential and kinetic energy, if you hopefully remember those topics. If you don't, you probably intuitively know that when Fonzie hits the teeter-totter, it's going to send Stu flying. So Fonzie is going to put some of his energy through the teeter-totter, and it's going to go into Stu, and that's why he's going to go flying. And we can manipulate or change how much of that energy gets transferred or how much energy there is by changing some things about Stu and Fonzie. But we're going to come back to that after we've discussed what potential and kinetic really are. On your notes side, I need you to make a little picture of a person with a ball on a hill, just like you see on your screen, and I need you to have everything else that's written on the screen as well. So energy is the ability to do work. We're going to come back to that a whole bunch. So if you want to make your car go, you have to put energy into it. If you want to lift some boxes and bring them to the top floor of a building, you have to do work to do that. If you want to tie your shoes, you have to do work to do that. And all the things that require work are things that require energy to make them happen. And we're going to get to this idea of work later. But for now, just know that anytime you want to do anything and make something happen, it requires energy. So potential energy is stored energy. It has the potential to come out. So if you have a ball sitting on the top of a hill, it has the potential to start rolling or start moving. And so it's stored at the top of that hill. If you want to think about it this way, it took work to get the ball to the top of the hill. And once it got there, we could leave it. And that work stayed there in the ball until it came rolling down. Kinetic energy is the energy of momentum. So kinetic energy is when things are actually moving or have motion. So let's think about the variables that go into potential energy. If you need to get a ball to the top of the hill, think about the things that matter when you're thinking about like what would make the ball easier or harder to make it to the top of the hill. Well, hopefully you're thinking first mass. If you had a really light ball, it doesn't take a whole lot of energy to get it up there, but if you had a heavy one, then it's going to take a lot more energy. So mass is one of the things that matters. And also how high the hill is. If you have to drag the ball up a mountain, that's going to take a lot more work than if you just had to bring it up like this little hill that's on your screen. So the two things that matter in potential energy are the mass of the object and the height that it's being brought up to. For kinetic energy, since it's the energy of momentum, and we've done a lot of things with momentum so far, hopefully you remember the things that go into momentum. It's the mass and the velocity. You can kind of think about it like if you were standing at the bottom of the hill, what would make the ball harder to stop? Well, if the ball is really heavy and going fast, that means that the ball has a lot of energy. So take a second and make sure that you have all of this information on your notes side. And when you're ready to go, I need you to answer this question over on the practice side. Can an object ever have both kinetic and potential energy? And I need you to explain. So pause this video, think about could an object, and if you could think of an example of an object, that would even be better, or a reason why the object can't, if you're saying no. Can an object ever have both? Pause and answer now. If you're still watching, I hope that you answered yes. So sometimes people forget that you can have two types of energy in an object. So think about like an airplane. When an airplane is just sitting on the ground waiting to take off, it hasn't got any energy yet. It's not off the ground and it's not moving. But then once it starts rolling along the runway, getting ready to take off, now it's got kinetic energy because it's moving, it's got momentum. And then the moment that the plane starts lifting off the ground, it has potential energy too. So anything that's moving above the ground could have both potential and kinetic energy. So now we're going to do some concept checks. There's nothing that you need to write down, but I do need you to pause this video and think about your answers before you keep going, because this is going to be really good practice for you for the next steps that we're going to do in a minute. So suppose that I have these two objects, these two blue blobs, who cares what they're made of, but notice that they're exactly the same size and that they're exactly the same height as each other, and they're being held over this ledge. What I need you to think about is who has the most potential energy. So as you're thinking about that, if you need to pause, probably you've got it though. So since they both have the same height, and they're both the same size, so in this picture, if they're the same size, they have the same mass. Since they both have those two things the same, they're going to have the same potential energy. They have the same potential to fall, or the same potential to turn into motion, or the same potential to turn into momentum. So which one would have the most kinetic energy right before it hit the floor? Hopefully you're thinking, well, we learned that gravity pulls all objects at the same acceleration. So as they're falling, they're going to go the same velocity. And so right before they hit the floor, if they have the same mass, and they're going to be going the same velocity, they're going to have the same momentum. So they're going to have the same kinetic energy right before they hit the floor. So that's the easy one. Let's change things up a little bit. Let's say that the two objects are now dangling above the floor. We haven't dropped them yet, but now they're in different positions. So answering the same kinds of questions. Which one's going to have more kinetic energy before it hits the floor? Now, pause the video and think about that. So as you're thinking about this, obviously the second ball is going to hit the floor first, but because it has a lot less distance to fall, gravity has less time to pull on it. One has a lot more distance before it hits the floor, so it's going to be going faster because gravity has more time to pull on it. So because 1 and 2 are the same mass, but one is going to be going faster, one is going to have more kinetic energy. Think about which one would hurt more if you had to put your fingers under there and let them crash into your fingers. Because one is falling from a higher height, it's going to hurt more. So now which one has more kinetic energy right before it hits the floor? As you're looking at these two things, maybe think about still which one is going to hit your fingers harder. If you have a much bigger object falling from the same height, Newton's law of gravity says that they're both going to fall at the same speed. They're going to hit the ground at the same velocity because they're being dropped from the same height. Remember back to the bowling ball and the feather video. But number 2 has a lot more mass, and so it's going to hit the ground harder. It's got more energy in it because it's got more mass. So number 2 has more kinetic. But which one's going to have more velocity before it hits the floor? They're going to be a tie because they both fall at the same rate. All right, now think about this. Suppose we just have number 1 just dangling there, and I want to place the second object somewhere. I'm not sure where I want to put it. Is it possible for a ball to be dropped from this height, where I have the question mark, and still have the same amount of potential energy as number 1? I want to put it right here. What do I have to do to the ball to make it have the same energy as number 1? Pause the video and think about that. So I want both of those objects to fall and have the same amount of impact when they fall and maybe hit my hands if they're down below. Since number 1 is starting from much higher, it's going to have to be smaller than whatever I put in the question mark spot. In other words, whatever I put in the question mark spot is going to have more mass in order for it to have the same energy as number 1. Is it possible for both objects to have the same kinetic energy at the bottom? And how about velocity? And explain that. I need you to do that, please, over on your practice side. So pause the video and answer that over on your practice side now. If you're still watching, hopefully you wrote down that they can have the same kinetic energy. Remember, kinetic energy is a combination of their mass and their velocity. So let's think about velocity for a second to answer that. They're not going to be able to have the same velocity because the height that you drop something from determines how fast it's going to be going. Whether you start with a little pebble or a big giant boulder, they're going to fall at the same rate as each other. So if I put something in the question mark spot, it's not going to go as fast than if I put something in the number 1 spot. So the velocity is going to be different. But I can make them have the same momentum when they hit the floor if I make the thing in the question mark have a lot more mass. All right, so let's go back to the warm-up question. Now that we've got some definitions written down about what potential and kinetic energy are, basically what we're doing is we're trying to say that Fonzie the elephant has got a whole bunch of potential energy that he's going to fall and hit the teeter-totter and turn Stu into a whole bunch of kinetic energy. So in order to make Stu go flying really, really fast, we're going to want Fonzie to be going a combination of really fast, and we want Fonzie to be really heavy so that he has the most energy possible. When it gets transferred into Stu, if Stu was really heavy also, he might have the same amount of energy as he goes flying away. But if we want him to go fast, we want him to be tiny. So Fonzie is big and fast so that Stu can be little and also fast as he goes flying off of the teeter-totter. Now we're about to get into the calculations. And let's do a quick review of what I'm pretty sure you've talked about in 7th grade, or if you haven't, let's introduce you to what some people have talked about in 7th grade. So as you look at this little race car as it goes through the loop-de-loops, look at the bars on the top. One of the laws in physics is that energy can't be destroyed. Energy has to go somewhere. You can turn energy into other things, but you can't get rid of it. So as this car goes around and around the track, it starts with a whole bunch of potential energy, stored energy, because it's way up high on the hill. But as it starts going down the hill, that potential energy is getting turned into kinetic energy. But the total never ever changes. And when it goes up the other side, it turns all back into potential energy. In real life, this wouldn't work very well because of friction, but friction turns energy into heat. Because if you rub your hands together, you can feel the warmth being formed between your hands. And heat is just another kind of energy that we'll talk about later. So we're ignoring all the friction in this situation right here. But what I want you to do is pause this video, and I want you to think about where on this track is potential energy the greatest, where is kinetic energy the greatest, and where does the car have both of the types of energy. So hopefully you've been able to identify a few spots. Potential energy is the greatest at the top of the hill because it has the most height. Kinetic energy is the greatest at the bottom of the hill because that's where all the potential energy got transformed. And then anywhere on the slope of the hill is where it's got both potential and kinetic because it's not done transferring from one to the other. In 8th grade, here's what we're going to do that's different than those topics. So in 7th grade, you talked about the concepts. In 8th grade, now we need to be able to calculate. We need to be able to actually say this is how much energy the object has at any spot on this track. So we're going to start with potential energy. And I told you that potential energy is a category of energy. So we're going to focus on a specific kind of potential energy, and it's called gravitational potential energy. It's the kind of potential energy that's stored because gravity could let it loose. So just like the big weight that's in this picture, it has the potential to fall because we had to fight against gravity to get it up there. Another kind of potential, just so that you can kind of think of the difference, is the gas that's in your car. The gas that's in your car has the potential to make the car move and give the car energy, but it's stored, it's waiting there, waiting to be used. So, to gravitational potential energy. The equation is up on your screen. I need you to be on your note side and do a really good job of copying down the information that you're about to have, because you're about to use this a whole bunch today, and later too. So potential energy is the mass of the object times gravity, because we have to fight against gravity, times however high up it is. When you multiply all three of these things together, we get our energy, the amount of energy that it takes. And potential energy is measured in this unit called joules. It's named after the first person who defined energy and gave it a measurement. And so he got the honor of having this unit named after him. And we use a capital J. For the mass, good old kilograms, just like we've been using in momentum. Gravity, as you hopefully remember, is 10 meters per second, and height is measured in meters. So once you have all this information, let's put this equation to work. Let's go and use it. So let's say that the mass in the picture, the red mass that's hanging, is 50 kilograms. And we raised it up to a height of 6 meters, and we want to figure out how much potential energy does it have. So we plug in all of the information that we were given. We were given a mass of 50, gravity is always 10, and we raised it up to a height of 6, and we just multiply. We get 3,000 joules. So the types of questions that you're going to have to do in this class that are a little bit tougher are what happens when we change something. So what happens to the potential energy if the height is cut in half? And also, what would happen if the mass is cut in half? So in order to figure out these kinds of questions, we need to make up some actual numbers. And since we just did the calculation over here for the weight, we can use those numbers, cut the thing in half, and see what happens. So if we're cutting the height in half, instead of 6 for the height, I put in a 3. We multiply 50 times 10 times 3 because it's half the height. And we find out that it's 1,500 joules, which is half of the energy that we had before. So in other words, cutting the height in half cuts the energy in half. Let's do mass instead. So if we cut the mass in half, instead of 50, we're going to go with 25, but we're still going to keep the other two numbers. So cutting the mass in half, we go 25 times 10 times 6, and we get 1,500 again. So cutting the mass in half also makes the energy cut in half. All of these things, the examples, need to be over on your notes side. Pause the video if you need to add those now. Now it's your turn to do a little bit of practice. Over on your practice side, please make a little sketch of these two shelves with a coffee mug, a cat, and a dog. All the masses for these three things are written down below here, and the three questions are on your screen. What is the potential energy for all three objects? Number 2, if the dog were to jump up to the lower of the two shelves, how would that change his energy? Like, how much energy would he add to himself if he did that? And number 3, how high would the cup need to be in order for it to have the same potential energy as the cat? So if we had to make the two things the same, where do we have to put the cup to give it the same energy as the cat? Pause this video and try those out on the practice side now. Okay, let's go over some answers. So starting with number 1, the potential energy for all three objects. We're going to be multiplying the mass times gravity times the height of the three objects. And what we get are the cat has 27, the mug has 15, and the dog has 0 because he's just sitting on the floor. He doesn't have any height, and so he has no potential energy. So for number 2, if the dog were to jump to the lower of the two shelves, how does that change his energy? So we're going to take the dog's mass times gravity times the height of that shelf, which is a meter, and we find out that he would add 24 joules to his energy. Now for the toughest of the three. Where do we have to put the cup in order for it to have the same potential energy as the cat? So in order to solve this type of question, we have to take the energy of the cat, which was 27, and we have to plug it into the potential energy equation. So we're going to say 27 equals mass times gravity times height. And we're solving for the height. We're trying to find the height of the cup. So if we want 27 to be the cup's energy, the cup's mass was 0.75, gravity is still 10. Now we solve for h. We're going to multiply the 0.75 times the 10, and then we're going to divide by the 7.5 to get 3.6 meters. So you would have to lift that cup fairly high up into the air to give it the same energy as the cat. Now we're going to go over to kinetic energy. So back over on your note side, we need to have the equation for this. So kinetic energy is the energy of momentum. And we usually talk about how much kinetic energy an object has right before it crashes into the ground. So this red mass the line was cut and it came crashing down and it hit this stump down here. And the reason why it had energy right before it hit the stump is because it had momentum. I told you a little bit ago that energy can't be destroyed, so once it hits the stump, all that energy is going to be transformed into other things like sound and heat and the motion of the stump going into the earth. And like we did in the last unit, it's going to change the momentum of the earth just a teeny tiny bit, but it didn't disappear. The momentum or the energy went somewhere. So let's get into the equation. Kinetic energy is 1/2 times mass times velocity squared. If you're interested in where this equation even came from, like why a half? Why is the velocity squared? There are a ton of really good YouTube videos out there that will explain how the math came to be, but it's not technically part of this class, so I'm not going to get into it with you now. But those resources are easy to find out in the world. So let's talk about the math here. One important thing to add to your notes, because I usually see this as a mistake, is that you have to do all your squaring first. When you're solving these kinds of equations, you have to do the squares first before you do any multiplying. Otherwise, you're going to get some wrong answers. If you're ready to move on and you have these things on your notes page, let's go ahead. Otherwise, please pause and make sure you have this information on your notes page. Let's do an example. So that mass that was falling and hit the stump, if it has a mass of 50 and was moving at a velocity of 12, we want to figure out how much KE, or kinetic energy, it has. So we plug in the things that we know. 1/2 times 50 as the mass times 12 squared. Remember, we have to do the squaring first. So we're going to do the 12 squared. In our calculators, we get 144 times 50 times 0.5, and we find out that the kinetic energy was 3,600 joules. Now we're going to do the same thing that we did last time, where what happens if we cut the mass in half? Or what happens if we cut the velocity in half? I want you to pause the video, and just in your mind, you don't have to write this anywhere, I want you to make a prediction. Do you think that it's going to have the same outcome as potential energy, or do you think that it's going to be different? Pause the video now and think about that. All right, let's check them. So if we cut the mass in half, instead of 50, we're going to have 25. Still going to do our squaring first. So 12 squared is 144 times 25 times 1/2, and we get 1,800 joules, which is half of 36. So cutting the mass in half still cuts the energy in half, just like we did in potential energy. So no matter what happens, whichever energy you're looking at, if you're using an object that you've cut the mass in half, you're going to cut the energy in half too. Now let's look at velocity. Velocity is a little different because instead of multiplying, like we did with mass, velocity gets a square, which changes things quite a bit. So for kinetic energy, if we cut the velocity in half, we go from 12 to 6 this time. We still do our squaring first. We're going to get 36 times 50 times 1/2. When we plug that into our calculator, we get 900 joules. So that means that kinetic energy was cut to 1/4. So let me say that again. When you cut your velocity in half, the energy is cut by 1/4. So what that means is that in kinetic energy, changing the velocity of your object has a much greater impact than it does when you change the mass of your object. If you need any of these examples still put over onto your notebook, please pause the video and do that before moving on. Now it is your turn to do some practice. On your screen, there are 2 practice questions up at the top and then an honors question down below. If you are in a grade level class, you need to do the first 2 for sure. And if you're feeling confident or comfortable with the topic, try the honors questions. If you're in the honors class, I need you to please try all 3. For the third one, where you're doing the one about Missy to water, I've left you a hint. When you set up your equation, you're going to have a square. You're going to have a square that you have to undo. You're going to have a variable like x squared. And in order to undo a square, you have to do a square root. So pause the video and try these 3 questions over on your practice side now. Ready, go. If you're still watching, you have tried the 3 questions. Here are all of the answers up on your screen, and all of my work is shown too. So if you need to pause the video to check those, please do that now.